Now, colligative properties. Those properties which depend upon number of solute particles are called colligative properties. And here remember, the solute is supposed to be non-volatile solute. That is a solute which will be, it will be a non-volatile solute, that is which does not undergo chemical reaction with the solvent. And in colligative properties, they do not depend upon nature of solute particles. Okay. Now, to mention, there are 4 colligative properties. One is, I always in fact start with lowering of vapor pressure, because most of them are dependent on lowering of vapor pressure only, or rather vapor pressure only. Lowering of vapor pressure. Number 2, elevation and boiling point. Number 3, depression and freezing point. And number 4, osmotic pressure. To start with, we'll take up the first colligative property which I had mentioned over here, and that is lowering of vapor pressure. Right. Now, before we delve into the lowering of vapor pressure concept, let's understand what vapor pressure is. Okay. Now, let's take a beaker and let's add some solvent to this. Okay. These are the particles of the solvent. Supposing the solvent is heated. You heat the solvent, right? The heat may be external, that is, you're externally supplying heat, or supposing you've kept this under sunlight, that is, somehow it is getting some heat. Now, what will happen is these particles, they will undergo random motion. They'll start moving. The kinetic energy will go on increasing. And when the heat that is being supplied to them, it goes on increasing, some of the particles, their kinetic energy will increase to such an extent that they will start converting into vapors. Okay. They will start converting into vapors and they'll start rising. Now, the particles which are converting into vapors, some of them will also, return back into the beaker. They will condense back into the beaker. Condense back into the beaker. A time will come when the rate of condensation will be equal to the rate of vaporization. Now, one thing that you have to understand is, and that is, the particles which are converting into vapor, they are this vapor which is on top of the liquid. It is exerting some pressure downwards. And when condensation is in equilibrium with vaporization, at this time, the pressure which is exerted by vapor, that is called vapor pressure. So when the vapor is in equilibrium with its condensed particles, the pressure exerted by the vapor on the solvent, that is called vapor pressure. Now, what is actually lowering of vapor pressure? Let's understand that. Better these in this beaker which we had taken, initially you just had solvent particles, and these solvent particles, they were free to move about throughout the length and breadth of the liquid. Throughout the length and breadth of the beaker. So they were free to move about. You supplied heat to them, or they were under sunlight. That is, somehow they were getting some heat, and they were moving randomly throughout the beaker with nothing to obstruct them. All of a sudden, what you do is you add some salt particles. It is just like you are in a room with nobody to stop you, and you are running from here to there, and all of a sudden some people, they enter the room. Obviously those people who enter the room, they'll be acting as obstacles in your path, and you will not be able to move freely about the room as you did before the entry of those people. So when these solute particles, and remember, these solute particles are supposed to be non-volatile, that is, they will not undergo any chemical reaction with the solvent, right? So when these solute particles, they are made to enter the solvent, these solute particles, they act as obstacles in the path of the solvent, and the kinetic energy which the solvent particles had previously, this kinetic energy gets low. They do not achieve that kinetic energy. The kinetic energy gets decreased, or it becomes quite low. As a result, the amount of vapor which is being formed now goes down. It becomes quite less. Okay. So with the entry of the solute particles, less number of solvent particles, they form vapors, and as a result, the pressure exerted by the vapors, it decreases. There's a lowering of the vapor pressure of the solution. Now, of course, because now you have the solution. Previously, you just had the solvent particles. Now you had now you have solution. So the decrease in supposing, let's derive the expression for this. Supposing P0, this is the vapor pressure of pure solvent, right? And let's say PS, this is the vapor pressure of solution, right? So lowering of vapor pressure is this will be P0 minus PS. Now Rawls gave an expression regarding relative lowering of vapor pressure. Now whenever we add this term relative, it means a ratio. That is, it is a comparison. Comparison between the vapor pressure of solution, or the decrease in vapor pressure, with the original vapor pressure of solvent. So relative lowering of vapor pressure, this is equal to P0 minus PS upon P0. Now according to Rolle's law, this P0 minus PS, this is equal to mole fraction of solute. Okay, now supposing small x is number of moles of solute and capital X is number of moles of solvent, right? So we can say P0 minus PS upon P0, that is equal to small x upon small x plus capital X. Now because in the solution, it's a dilute solution. Remember when we discuss colligative properties, we actually take into account dilute solutions. So this is very, very less than capital X. So in the denominator, we can ignore small x. So P0 minus Px upon P0 is equal to small x upon capital X. Further, if small w is the mass of solute and capital W is the mass of solvent, small m is the molar mass of solute and capital M is molar mass of solvent. Then P0 minus PS upon P0, this is equal to small w upon small m whole upon capital W upon capital M, or it can be written as small w capital M upon capital W small m. Now this is the expression of relative lowering of vapor pressure. I hope you've understood the topic, and in our next video we'll be discussing numericals related to this and also the next colligative property. Thank you so much.